Put you down. Okie dokie. Let's go ahead and get started. So today we are going to start chapter 10, which is stoichiometry, a fancy word that we're going to learn. Actually, we won't really be learning the word stoichiometry because it more describes a process that we're going to be doing for the next couple of days here. Intro, I think this is chapter 8. But also, if you are using Tro, you'll also have parts of it from, let's see, I think there's going to be some in 11, 12, and 13 also. So what I've done is I teach the states of matter first. Tro teaches them after teaching stoichiometry. So he has put stoichiometry problems in those later chapters that will relate to those specific phases. But since I've already kind of gone over all the different phases, we're going to tackle it all at once here because it's really the same exact procedure that we'll be doing this entire time. Good morning, Brittany. Let's see. Today I do have Momo somewhere in the room here, so maybe she'll make a guest appearance later. So, so far we've talked about chemical reactions. We've done so much stuff with them, right? We've balanced them. We've done redox stuff. We've done net ionic equations. We've figured out types of reactions. We've seen evidence of reactions. We've been able to predict the products of reactions. We've done so much. So what we're going to do today is going to be learning how to kind of apply these reactions. So a particular reaction that you may be aware of is a recipe. Let's see what I'm missing. Butter. This is a recipe for a famous cake called a pound cake. A pound cake is made with, yeah, exactly. So a pound cake is named as such because all of the ingredients are 1 pound each. So it is a cake for sure. So yeah, definitely. So this is kind of the most common way to introduce students to stoichiometry is through recipes. I believe Tro uses like pancakes in the textbook. I think I use sandwiches, but today we're going to use pound cake, because why not? So this is essentially a chemical reaction. We have 4 reactants that are combining to make a cake. We're going to have to heat this, of course. This is an endothermic reaction, not necessary for this particular step. But we're going to be able to use this to kind of see how much of our ingredients we're going to need if we want to produce a certain number of cakes. So for example, if we want to make 4 cakes, how much butter do we need? And so what we're able to see here is that we're going to have 4 cakes is the information we're starting with. And we're going to use, guess what, conversion factors to figure out how much butter that we're going to need. And we're going to see this is exactly the same thing we're going to be doing with chemical reactions. So if we look at our reaction here, it's telling us that for every 1 cake, we need 1 pound of butter. These here are our reaction coefficients. And so if we do this very difficult math here, 4 times 1 over 1, it's telling us that we need 4 pounds of butter. So this is stuff you do all the time. If you want to double a recipe, you just double all the ingredients, right? If you want to make 1.5 times a recipe, you would multiply all your ingredients by 1.5. And so if we want to make 4 times the recipe, we would need 4 times the number of this particular reactant here. And so we can have stuff like that we're going to see how to do. Another one, perhaps one that is more, I guess, applicable to real life, is if we have let's see, what were all our ingredients? I can't remember. Sugar and 3 pounds of butter. How many cakes can we make? Yeah, right. You're actually, yeah, forget the lab project. Just make me some cakes. And that's what I'll judge you on. That is chemistry, so no problems there. Yeah, by the way, those lab topics will be coming out today or tomorrow once I finish writing them all. Your class will be easier because there's only 5 groups, I think, so that'll be easy for me to come up with projects for you guys. So expect that either today or tomorrow. All right, so let's look at this question here. It's telling us we have 2 pounds of eggs, 4 pounds of flour, blah, 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 blah. And we want to know how many cakes we can make. Yeah, right? Wouldn't that be nice? So with this, you want to look at each ingredient by itself. So let's start with our eggs. Yeah, you're exactly right, Brittany, but let's see how we can do this mathematically. We would know our recipe told us it was 1 pound of everything. I'm not going to scroll up just because all of them were 1 pound. And so this was 2 cakes. So again, our pound of eggs cancels out. We're left with cakes. If we do the same thing for the others, flour is next, sorry. That's going to be 4 cakes. If we do sugar, I'm just going to say that's 5 cakes. And then the butter would make 3 cakes. So if we look at this, Brittany has come to the conclusion that we can only make 2 cakes. And that is absolutely correct, because once we make our second cake, we are out of eggs. We do not have any more. We cannot make any more cakes. So we're going to see that when you have different quantities of your reactants, you're always going to choose the one that has the smallest amount of product. So because at that point, you'll have run out of that. So we're going to see situations like this more towards the end, so probably tomorrow. So let's see, someone's trying to get in and Momo's trying to escape here. All right, Momo, calm down. Actually, let's see. No, Kaz opened the door for Momo. That's pretty funny. This little, 6-pound chihuahua opens the door for the Akita. Go figure. And now she's gone out. So we'll see this situation a bit later when we have multiple different amounts of reactants. So let's go ahead and see what this looks like in terms of an actual chemical equation. So let's see. One of my favorites to use for this. Here's a chemical reaction for us. Very important process. This is the reaction that produces most of the world's fertilizer. Very important reaction to have here. What this reaction tells us is that we need 3 molecules of H2 and 1 molecule of N2 to make 2 molecules of ammonia. That's what the coefficients mean, of course. So we would need 3 hydrogen molecules, 1 nitrogen molecule, and we would make 2 ammonias. That's what the reaction coefficients tell us. So again, this is just your reaction coefficients. We're going to see that this is exactly the same as saying we need 3 moles of hydrogen and 1 mole of nitrogen to make 2 moles of ammonia. The ratio would be the same. So the reaction coefficients will tell us exactly kind of how many parts of each reactant to make however many of our product. So just like with the cakes, if we had, a dozen pounds of all of those ingredients, we could make a dozen cakes, right? If we had a mole of all of those pounds of eggs somehow, we could make a mole of cakes, right? So mole, dozen, it's just another word for a big number, right? So this is the stuff that we're going to be focusing on in this kind of chapter here. So what this tells us is that we can come up with some reaction or conversion factors. For this reaction, we're going to see that for our purposes, we would need, for every 3 moles of hydrogen, 1 mole of nitrogen. And so this is going to be a conversion factor that we get out of this. And we could say the same thing. We would need 3 moles of hydrogen to make 2 moles of ammonia. Stoichiometry. Up here, stoichiometry. Okay. And the last one we would get, I guess, would be moles of nitrogen is 2 moles of ammonia. So this is just all those reaction coefficients. Perfect, Brittany, yes. So this tells us if we had 5 moles of hydrogen, let's say 5.0 just to put some sig figs in there, how many moles of oh goodness, Kaladin, what are you doing in here? You're too crazy to be in here during class time. So if we had 5 moles of hydrogen, how many moles? One moment here. Go outside, dude. Get out of here. Relax, Kaz, you're okay. We could see how much nitrogen we would need to react with it. Yeah, right? That's probably why. So we are going to set this up just like any other dimensional analysis. The only thing that we're doing here is we're using our reaction coefficients. So technically none of this stuff that we're learning in this chapter is going to be new except towards the end. We're going to have kind of one thing that's new here. But all of this stuff is just kind of combining information from other chapters, things we already know. So this is telling us we would always, of course, start with how much we know. We know that we have 5 moles of hydrogen. We're going to multiply it by something to get moles of nitrogen, right? And so we're going to go ahead and look at our conversion factors up here. Again, these are just the reaction coefficients. And we're going to choose one that we're going to need for this. So do we have a relationship between hydrogen and nitrogen? Of course we do. It's the very top one there. So we're going to need to... sorry, let me see if I can fit this all. Yeah, I can. Okay, good. Which one is going to go on top and which one's going to go on bottom here? Absolutely. So this is the ratio of nitrogen to hydrogen in our reaction. Perfect. Absolutely. And so 5/3 is what? 1.6? And so that number here, let me just move this over, would be 1.66. So I'll just round to 1.7. So we would need 1.7 moles of nitrogen in order to react all of that hydrogen. Hooray! And here's part B for this question. We could see how much ammonia is produced as well. So it would be kind of exactly the same setup. So we would start with our hydrogen. We're still going to have the same thing on the bottom because that's our reaction coefficient. That's not changing. So let's go up and see what the coefficient was for ammonia. My gosh. We see here it's 2, right? Hydrogen was 3. Ammonia is 2. So we're going to need 2 for ammonia. Notice, as always, our units cancel out. They also canceled out before. 5 times 2/3. Let's see. Can I do that in my head? 10/3, so that's 3.3. And so you would get 3.3 moles of NH3. And notice that just because of rounding, that should be just double of what the nitrogen was, right? Because nitrogen had a coefficient of 1, ammonia had a coefficient of 2, so we would expect to make twice as much ammonia as there was nitrogen in there. And again, that makes sense because we have 2 nitrogen atoms in our nitrogen gas, and we have 1 nitrogen atom in our ammonia, so we would expect we would be able to make twice as much ammonia from a given amount of nitrogen. How exciting. So, purple time for our big kind of point here. The only way to change different molecules or different substances in our mathematic stuff, which we call dimensional analysis, which is just all this math stuff, we must, or rather, I guess I should be grammatically correct with this, is to use the reaction coefficients. So what this means is that we can use chemical reactions as conversion factors between moles of one substance and moles of another substance. So whatever those be, I just put A and B because they can just be placeholders. We did it for moles of hydrogen and moles of nitrogen. We also did it for moles of hydrogen and moles of ammonia. So whatever your A and B happen to be. This here is your reaction coefficient. This is the conversion factor that is going to be utilized to swap between different substances. It's the only way to do that. So you can never say, you can't just go, grams to grams or something. You have to use these reaction coefficients. And here's where the fun stuff comes in. We have studied many, many different ways to get moles of something, right? We, of course, we could have a massive substance, right? And we know how to go between mass and moles. Okay, Oz is just scratching at the door. Let him in. Come on, no, not you, mister. You're gonna make Kaz upset. Come on, Oz. Go do it. They're being particularly rambunctious today. How do we go between mass and moles again? Notice we can do the same thing for B. Who remembers how to go between moles and mass? Exactly, Lamonda. Perfect. So if we had moles of A, we could go make grams of A, right? Using the molar mass. And same thing with B. So if we had moles of B and we wanted to find grams of B instead, we would use the molar mass of B to figure that out. How about, what if we had the volume of solution of A or B? If we had a solution of A instead. We had another conversion factor. Let's see, I'll use light blue for this one. This was molarity, right? Molarity is how we could go between a volume of solution and the moles of that, right? That's a concentration term. So how many moles are in that volume? And so molarity would be another conversion factor that we could use to find the volume of solution. So you're seeing kind of maybe this is all somewhere in your brain coming back to you. The part on the right is illegible. It's off the screen. Like you guys can't see this happy face. I'm watching the stream as well on my other monitor, and I can see everything. Okay, not sure what's happening, Maya. Okay. And so we have one more. So I'll spoil this for you guys. We have one last one. And this would be the pressure or volume of a gas. So I could give you a volume of a gas, provided I provide you with the pressure and temperature as well. But guess what? We have all this stuff we can do. I guess I should write this gas A will be consistent. Oh, maybe try tilting your phone to the side. What was the conversion factor for this one, by the way? What the heck are we going to do to go between pressure or volume and moles if it's a gas? Um, so I'm gonna have to use the whole page for all these. Just it's gonna be way too messy. Um, try shrinking it perhaps. Or you could maybe watch it on YouTube. Yeah, exactly, Brittany. That's exactly right. You would use the ideal gas law here. So this is a very important, um, very important little chart here. I guess we have. This is oh good, okay. So this is all we're doing this chapter. So we're going to be looking at how we can change these quantities of various substances into quantities of other substances. And we're always going to follow this kind of chart. So maybe one time we'll go through. I'm out of colors here, but let's see. How about orange? Maybe one time we'll start with, a a gas, and we'll end up wanting a mass of B. So let's say I start with pressure of A, and I want to find mass of B. This is the route we would go. We would go from pressure to moles of A, use our reaction coefficients to get moles of B. For moles of B, we'll use our molar mass of B to get mass of B. So just to erase this, because we don't need that, we could also start with mass of A and end up with mass of B. We could totally do that too. So we're going to see we have all these different potential routes we could do. So we could go from mass of A to mass of B, going through moles in the middle. We could go from volume of A to mass of B, going through moles in the middle. We could go from mass of A to volume of solution B, guess what? Using moles in the middle. So, okay, yeah, I will try to avoid that, but I can't guarantee it, so. Okay. So, that's the idea here. We're going to just be using this chart for the rest of the chapter. All right, so this would be a good, thing to screenshot or something. Important little bit here. Okay, so let's see this in practice. Let's get a reaction going. How about we let's see, what reaction shall we do? How about we do hydrogen peroxide breaking down into these. I guess I should balance it for you guys. So these ones would probably already have balance for you on an exam, because these ones we're not focusing on balancing. These ones we're focusing on the mathematics here. So let's see, if let's say you have 50 grams of hydrogen peroxide, what mass of oxygen can you make? So let's go ahead and do a plan for this. Let's see what we can do. We have grams of H2O2, and we want grams of oxygen, right? How are we going to plan this one out? Well, let's go ahead and look back up at our chart here. What's the pathway we're going to be doing? We have, back to orange, we have mass of A, right? And we're looking for mass of B. So, of course, we have to go through the middle. And that's going to be this path right here. So we're going to need the molar mass of A, the reaction coefficients, and the molar mass of B. And that's all we're going to need to figure out this problem. So let's go ahead and get rid of the orange here, just so we can keep using that chart. So this is going to be the plan for this unit conversion here. So this was our molar mass. These are our reaction coefficients. I don't know how to spell coefficients. Coef. There we go. And this was, again, a molar mass. Will be our last conversion bit. Alrighty, so let's go ahead and do this. I'll just tell you the molar mass of hydrogen peroxide is 34.02 grams per mole. Yeah, grams per mole, exactly. And then this one is, of course, 32 grams per mole. They're becoming more and more frequent, it seems. Okay, let's go ahead and work this out. So we have 50 grams of hydrogen peroxide. We're going to want to use our molar mass. We have grams already, so grams should go on the bottom. Excellent choice, Maya. That is exactly what I would suggest. Just ignore that nonsense there. So 34.02 grams should go on the bottom. 1 mole on top. Of course, we should always, with these, you're going to want to make sure you are consistent with putting which substance you're working with, because now we're introducing math with multiple substances. Next thing would be our reaction coefficients. So let's go ahead and look at our reaction. Since this problem we're looking at hydrogen peroxide and oxygen, that's 2 and 1. 2 moles hydrogen peroxide and 1 mole of oxygen. So peroxide should go on bottom, so that it cancels out. So we'll have our 1 mole of oxygen on top. And then our last step here would be our molar mass for oxygen. And that's it. We just need to do this math. Let me go ahead and do that real quick. So we have 50 divided by 34.02 divided by 2 times 32. Doing all that stuff, we get 23.5 grams oxygen. Let's let's double check our units here. Make sure everything cancels out. Grams of hydrogen peroxide cancels out. Moles of hydrogen peroxide cancels out. Moles of oxygen cancels out. We should be left with grams of oxygen, which indeed we are. So we see here the only new thing here for us is that part in light blue. That is our reaction coefficients. That is the only new thing that we're using here for our unit conversions. And so it's very beneficial for you. I know it's tedious, but it is very beneficial to write out the formula of your compound every time for every conversion factor here. That way we know exactly, we're still working with hydrogen peroxide, and then we can switch to oxygen, and now we can do units with oxygen in them. Now Oz wants to go outside. Forget it. He can stay in here. Alrighty. Any questions on that one? All right. Get ready for part B. You would probably need to do it yourself. I'm not going to be giving you compounds that are going to be terribly complicated. Like H2O2 is, it's two numbers to add up, right? Nothing too crazy. So that shouldn't be a huge time concern. So I would expect you to be able to do the molar mass of a small molecule on the exam. I'm not going to give you some crazy 18 carbons and 52 oxygens and blah blah blah. We'll keep it reasonable. Okay? Otherwise, sure, I'll give you the molar mass if it's something more complicated. All right, here's part B. Oxygen is a gas, right? Oh. Yeah, so you'll be dealing with stuff, like this oxygen stuff. These are not complicated, fancy molecules here. So these should be easy for you to work with. I'll give you plenty of complicated molecules on your homework. You can do all that, because you'll have so much time to do that. Right? Okay, so let's look at this one. What volume of oxygen is produced if the pressure is 1.2 atmospheres and the temperature is 300 Kelvin? What the heck are we doing here? So let's go ahead and look at our chart again. Our lovely, lovely chart. We are now looking for the pressure or volume of a gas. And again, we're given the mass of hydrogen peroxide to start. It's always a good idea to still use the information you're given in the problem if you have multiple parts, just to eliminate the chance of errors happening. So if we were to calculate our mass of oxygen incorrectly, maybe that could have a problem that would lead us to get the other one wrong. Yes, we're always going to use that R. So let's go ahead and see what we're doing here. Bloop. So we're going to start with our mass of A and molar mass. We already have those. That's hydrogen peroxide. We already have our reaction coefficients as well. So the only thing new we're doing here is we're applying the ideal gas law to this as well. So let's go ahead and get rid of the orange before I forget. So if we plan this out, it's always a good idea to start with the original quantity that we're given. So that was the hydrogen peroxide mass that we had before. So we would convert that to moles, just like before, into moles of oxygen, and now into liters of oxygen, a volume. So like before, we're going to do the first part exactly the same. We'll have our molar mass there. We'll have our reaction coefficients. Why do I always forget the E? Maybe I can salvage this. No, that's just disgusting. Okay. Coef. And this one now is our ideal gas law. That is our conversion between moles and liters. If you want, if you are confident, you can just take your grams of oxygen here and get moles. That is a liter, L. So volume. This part here. So this first part is all identical, oh my gosh, to last time. All this stuff that's underlined here is exactly the same. We're just now taking our thing and going, instead of mass, we're going to go into liters instead. Why not? We can do all sorts of crazy stuff. So we started with 50 grams of hydrogen peroxide. What was it, 34.02 grams for 1 mole? We had our reaction coefficients. Okay, so all that part was exactly the same as before. So let's go ahead and see what our moles is going to be. And then we can plug that into our ideal gas law. So 50 divided by 34.02 divided by 2. So this is 0.73486 moles of oxygen. Looks like we have 3 sig figs, so we'll just remember that. Where the heck did this go? And so, since we are using the ideal gas law here, we know that we are looking for a volume. Yeah, exactly, Kenji. Perfect. So the volume is nRT over P, just moving the P to the other side of the equation. Just going to put this down one step. 0.73486 moles. 0.08, oh gosh. Just like Brittany said, yes, we are definitely still using our same R as before. Temperature was what, 300? Yeah. And the pressure was 1.2 atmospheres. So always let's double check our units. Grams of hydrogen peroxide canceled, moles canceled. We have moles of oxygen. Moles will cancel. Kelvin will cancel. Atmospheres will cancel. We'll be left with liters. Perfect. Is that right, Brittany? Okay. Brittany has done the math for us. She got 15.1 if we do our 3 sig figs. And that is liters. Honestly, that looks reasonable given the mass we had. So we had a little bit less than a mole here, right? And this is pretty close to STP. And STP, remember, is 22.4 liters per mole. So this is pretty reasonable. I don't think you've done anything wrong. But let's double check if you insist. 0.08206 times 300 divided by 1.2. Indeed, I got exactly what you got. Awesome. Hooray. So you see here, the whole point of all this was we can do all sorts of crazy stuff. We can figure out all these different quantities now that we can have produced in a reaction. Any questions on that one? So, cool. Okay. How about another one? One of our favorite double displacement reactions also happens to be a neutralization, right? We are producing water. So, standard acid-base reaction. Let's say we had let's see. Let's say we're given this. So we're doing some solution stuff right now. Looking at this, we have a volume and a concentration of sodium hydroxide, and we have a concentration of sulfuric acid, and we're being asked what is the volume of sulfuric acid that we're going to need to react with this sodium hydroxide. So, if we look at this, remember we always want to say kind of like A is the one we know everything about. We know everything about sodium hydroxide. We know a lot of information about that. The one that we're looking for is going to be B, right? Just if we want to look at our chart. So let's take note here. We have a concentration and a volume of A, solution A. And then we have a concentration of solution B. So let's go ahead and go back up to our chart, as always. So we have a volume of solution A, and we are looking for the volume of solution B. So it looks like we're just going to go straight through the middle here. And so we can see here, oops, the I forgot to circle our conversion factor there. So we can see here our plan would be that we're going to use the molarity of A, then the reaction coefficients, and then the molarity of B. And we're going to get there our volume of solution B. Okay, so you see how, again, we're using the chart to go through this. And now we're going to hide the chart. So let me just go ahead and write out what we just said. So we are starting with volume of A. Oops. We are going to moles of A. We are then going to moles of B. And then to volume of B. What am I saying A's and B? Well, I've already written A and B up here, so we're okay. We know which one's which. So this was the molarity of A, the molarity of B, and of course this is our reaction coefficient. There is kind of one more step on each side that we're going to see. What's the unit of molarity again? Could someone remind me? What did molarity mean? Indeed, volume bottom, but what unit, Brittany? What are the units here? Yes, that's the thing we're going to need. Yes, absolutely. So remember that molarity is moles per liter. However, we are given milliliters. So we'll also want to work that into our problem. We need liters of NaOH, not milliliters. That's just the little aside here. So if we're going to set this up, 42.62, okay. We're going to want to get rid of these milliliters. Oh, did it freeze, Kenji? I see it has the last thing. So I saw Lamanda say liters and Brittany say milliliters to liters. And then you said the chat froze. So if that's what you see, then, excuse me, you should be okay. Very nice. We can just continue, though. Brittany, you're totally welcome to do it in a separate step and just use that liters as is. But let's go ahead and just do the whole thing. And shame on me, I have omitted my substance. So now we're in liters of NaOH, which means we can use our molarity. This is going to end up going down one line. I hope you forgive me. But long problem, I guess we could say. Now that we have moles of NaOH, we're going to use our reaction coefficients. So we have done this part. Now we're going to use our reaction coefficients. It's right here. Our reaction coefficient for sodium hydroxide is 2. Reaction coefficient for sulfuric acid is 1. Sodium hydroxide goes on the bottom. We'll get our moles of sulfuric acid. I really wanted to fit the last part in here, but I ran out of space. So we're gonna do this. Sorry. Only so much space, right? So if we have moles of sulfuric acid, we were going to use the molarity of sulfuric acid next, and that was 2.12. Oops, except this is upside down. Shame on me. So we saw H2SO4 is on the top previously, so that's why it had to be on the bottom for this one. So that's where I had switched them accidentally. And since we're asked for milliliters, we'll go ahead and do the same thing before that we saw. So again, this is just unit conversion. You thought we would be done with that. No, never. We're never done with unit conversion. Wow, that was long. But let's double check all of our units make sense. That's going to make sure you know everything that needs to be on the top is where it should be. Everything that should be on the bottom is where it should be. So milliliters of NaOH cancels out. Liters of NaOH cancels out. Moles of NaOH cancels out. Moles of sulfuric acid cancels out. Again, sorry that it's in two separate lines here, but ran out of space. And liters cancels out. We are left with milliliters of sulfuric acid, which is what we were asked for in the problem. Hooray. Of course. course this was at times. Wow, let's go ahead and do all this math. 42.62 divided by 1,000. Multiply by 1.25. Divided by 2. Divided by 2.12. Times 1,000. I guess we could just ignore the times 1,000, but that's okay with the divide 1,000. Doing all this fun stuff, we get 12.56 milliliters of H2SO4. Doing a quick sig fig check, though, it looks like we're going to need 3 sig figs, so let me go ahead and round it for us. Woo! That was exciting. Perfect. Absolutely right, Kenji. So what Kenji is doing, I would very much recommend you do as well. Always kind of do these on your calculators too, to make sure that you can input everything correctly, just so you're familiar with how your calculator works. Everybody's calculator is slightly different, right? So I would definitely recommend actually doing these calculations yourself. All right. So with the 3 minutes we have left, here's part B. There's always a part B, right? Nice job, both of you. Excellent. We could also find the mass of... So I'm going to... You know what? Let's go ahead and just do this one tomorrow, I think. I don't want to rush you guys through this one. So, yeah, let's just go ahead and save that one till tomorrow, perhaps. But you know what? Go ahead and, for later today, just try it out. See if you can figure out what the mass of Na2SO4 is that's going to be produced by this. In grams. You're going to do exactly the same stuff on top, except instead of using your molarity of B, you're going to use molar mass instead. And that's it. That's the only difference. So you can find out so much information using this stuff. Whew, exciting. Alrighty, well, we will continue doing more of this tomorrow. So, yeah, think of, if some of the stuff is going crazy, go ahead, bring questions tomorrow. We can go over them again. We're going to continue otherwise tomorrow. Remember, Wednesday is a holiday, so we are not going to have a stream. I think they're already open, Lamanda. I did already upload them because I had those ones done. Let me just double check. Let's see here. Canvas for you guys. They are available November 10th at midnight. Okay, so I guess why did I make it Tuesday? Okay, I'll make it now, so you guys will be able to see them. So both ones are available for you guys. There we go. Oh, Kenji, relax. Yeah, right. Excuse me. Okay. Alrighty. I guess I'll see you all tomorrow.